Okay, this is the second vodcast covering ionic and metallic bonding. This is kind of a longer section. You do want to have a periodic table handy for this, one that you can write on because I'll have you labeling some things on it. Okay, so an atom can have core and valence electrons. Okay, core electrons are anything that's not valence. In the last section, we learned about valence electrons. Those are the outermost electrons in the S and P subshells, and those are the ones available for bonding. Core electrons are found close to the nucleus, but it's valence electrons that that are responsible for the chemical properties of atoms and different compounds, and it's valence electrons that are responsible for holding two or more atoms together using a chemical bond. Now, we mentioned the Octet Rule last vodcast, and the Octet Rule states that atoms bond in such a way so that each atom gets 8 electrons in its outer shell. So that's the goal. Now, what we didn't mention before is that there's more than one way in order for atoms to achieve an octet. They can do so by transferring electrons from one atom to another, and they can also do it by sharing one or more pairs of electrons. So that's what's being shown in the diagram down here below. Okay, is you've got this M atom or this M ion with a positive charge and an N ion with a positive charge. And the positive and the negative are attracted to each other and they bond in that way. Here in the second little picture, I've got two N's, and what happens is they end up sharing their electrons with one another in order to complete those bonds. So your ionic bonds are formed when you have a complete transfer of electrons between atoms in order to form a compound. And then you've got covalent bonds when two atoms share electrons to make those molecular bonds. And in this section, we're going to learn about ionic bonds and another type of bonding called metallic bonds. In the next recording, you guys will learn about covalent bonds. Okay, so you can just see here in this diagram, you've got representative particles, which means we can have formula units or molecules. I'll give you the exact definition of those later on. And formula units form ionic bonds. That's where the positives and the negatives are attracted to each other. And then covalent bonds, this co means with, okay, and so that's part of the sharing there. So ionic bonds are held together by opposite charges through electrostatic attraction. This is a really important point for you to know. Okay, so the positives and minuses are attracted to each other, the positives and the negatives, and it's held together by electrostatic attraction. I'm telling you right now, you're going to see that on quizzes and midterms and things. Okay. When you have ionic compounds, the generic term for them are called salts. We're used to thinking of salt as NaCl, sodium chloride. That's table salt that you sprinkle on food and put in use while cooking. But pretty much any ionic compound is a salt. And that's when you have a positively charged ion attracted to a negatively charged ion. Now, these ionic bonds are done in the simplest whole number ratios, and when you have those, it's called a formula unit. They're not called molecules. Molecules are reserved for covalent bonding, but ionic bonds, those compounds form formula units, and that's another vocabulary word that you need to be familiar with. So it said before, ionic bonding is formed through the transfer of electrons. And if you recall, the electrons are achieved in order to, the electrons are transferred in order to achieve noble gas configuration, which is highly stable and desirable for atoms and compounds. So let's take a look here at trying to make sodium chloride, our table salt. Okay, metals lose electrons, nonmetals gain electrons. That's what you need to know. Okay, if you look at sodium on the periodic table, sodium has 1 valence electron, chlorine has 7 valence electrons. So you can see sodium will transfer its 1 electron to the missing empty hole right there for the chlorine. And so that nonmetal chlorine now gains 1 valence electron to fill out its outer level, and it accepts the one that sodium's going to lose. And then now you have this positively charged sodium and negatively charged chlorine that are attracted to each other through electrostatic attraction, and it forms a bond. So remember, when you have cations, no dots are shown, and with our anions, our dots are complete. Okay, let's do another example using calcium and phosphorus. Okay, calcium has 2 valence electrons and phosphorus has 5. Oops. Okay, we got to make sure all the electrons are accounted for so that each one has a noble gas configuration. Well, calcium has 2 it wants to get rid of. Phosphorus is looking for 3. So it's not quite as simple as our previous example with sodium and chlorine. So calcium's going to give away its 2 electrons to phosphorus. And now it has a 2+ charge. And phosphorus now has 7 valence electrons, but that's not quite enough. It still needs more. So we bring in another calcium, and that calcium transfers 1 of its valence electrons to phosphorus, so phosphorus completes its octet. But now calcium has a leftover valence electron. Right? So phosphide's complete, the P3-, but calcium's got a leftover valence electron. So what happens then is another phosphorus comes in, and that valence electron gets transferred over. Calcium's got a 2+. This phosphorus now has 6 valence electrons, so 1 more calcium has to be brought in, and it's going to transfer its 2 valence electrons over to the phosphorus. So now I have 3 calcium ions and 2 phosphide ions. And this is what's happening in ionic bonding. You know, it's just transferring electrons in order to complete its octet. So when we go to write our chemical formula, because that's what you're actually starting to do in this unit, is you're learning how to write chemical formulas. This is what it looks like. I have 3 calciums and 2 phosphorus. And so my chemical formula now is Ca3P2. And that whole thing is called a formula unit. Okay, so this is your first chemical formula here. It shows the kinds and numbers of atoms in the smallest representative particle. So it shows our kinds. We have calcium and phosphorus, and it also shows how many. I have 3 calcium and 2 phosphorus. And that's the smallest whole number ratio, meaning we can't divide and get smaller numbers. So here's where you need your periodic table to label. Okay, the valence electrons, I showed you how to count them in the last section. Okay, you've got 1 valence electrons, 2 valence electrons, 3, 4, 5, 6, 7, and 8 valence electrons. And remember, we just skip the transition metals. The transition metals kind of have their own rules. Okay, same thing with the intertransition metals, and they're not easy to figure out. So when we're going to do charges here, this group 1A is going to give away 1 valence electron, and it's going to have a +1 charge. Group 2A is going to give away 2 valence electrons, and it's going to have a +2 charge. So you should write these charges on top of your columns on your periodic table. Group 3A, or 13 right here, has 3 valence electrons. It's going to give them away. and have a +3 charge. We are going to skip group 4A for now, okay? And then we have 5A, okay? Group 5A needs 5 more I'm sorry, not 5A. 5A needs 3 more electrons, so it's going to form a -3 ion. Group 6A is only 2 away, so it's -2, and group 7A is a -1. Okay, we skip group 4A there with carbon because if you look, it goes +1, +2, +3, and then -3, -2, -1. So that group 4A in the middle can do both things. It can do a +4, it can do a -4. It actually also does some other things like a +2 and a -2. But how you figure that out, we'll deal with at another point. So what's the chemical formula when the following elements combine? Okay, so you need that periodic table you just labeled. Sodium is in group 1A. When it forms a charge, it has a +1. Okay, and when oxygen forms an ion, it's a -2. So we have to look, do these two cancel out perfectly? They do not. So I need to add another sodium to cancel out the oxygen. So now I have 2 pluses against a -2. And since that gives me 2 sodiums, it's Na2O for my formula. If I do the same for magnesium, okay, magnesium, if you look back at your periodic table here, magnesium has a +2 charge. So I have Mg +2. And then the chlorine, if you go back, look at chlorine. Here's chlorine. Chlorine is in the -1 column. It has a -1 charge. So Cl-. These two do not cancel out perfectly. I have a +2 and a -1. So Cl, I need another -1 there. So now I have 1 magnesium and 2 chlorine, so my formula is written as MgCl2, just like that. Now, when you are writing these charges here, chemists are huge fans of invisible ones. You can write the one like this, MgCl with a -1, and it's fine. But as a shortcut, you can write it just as a minus sign and it's assumed to be a 1. Same thing with the sodium. I could have written +1, or I can just write plus, and both are correct. Okay. What you really want to watch out for is you want to make sure that you're writing your element symbols properly. Okay. Do not write Na2O like that. We need to use a lowercase a for these. So you try 2 more. Try these last 2 and see if you can get them to work. So if you've got aluminum, aluminum is a +3 and sulfur is a -2. Well, I've got more pluses than minuses, so I need to add another sulfur. Okay, so now I've got 3 pluses and 4 minuses, and that's not going to work, so I need to add another aluminum. And now I've got 6 pluses for the aluminum and 4 minuses for the sulfur, so I need to make it 6 minuses. Now I have 6 pluses and 6 minuses, and they cancel out perfectly. That's what you're trying to do, is you're trying to cancel things out to make them neutral. Okay, so you want neutral charges. So now when I go to write my formula here, I've got Al2S, and I had 3 of them. So whenever you have that 3-2 combo, what they have in common is 6. Okay, so that Al3+, that goes into 6 twice, so I'm going to need 2 of the aluminums. And then the sulfide, the S -2, it goes into 6 3 times, so I know I'm going to need 3 of the sulfurs. So let's try the last one, gallium and fluorine. Ga, if you look back on your periodic table, find Ga, it's right here. It has a +3 charge. And fluorine has a -1. Check and see if they cancel out perfectly. Okay, these do not. I actually need 3 fluorines to cancel out that +3 of the gallium. So I have GaF3, just like that. You may be able to do these in your head, okay, and see that it's a +3 and a -1. You are welcome to do so in that case. All right. In fact, that's where eventually you'll be able to do these without drawing out the charges or writing down 3 Fs. You'll just be able to see what's needed. And that's appropriate. That means you're learning it and getting the hang of things. Okay, so let's talk about some properties of ionic compounds. They are crystalline solids. What that means is they have a regular repeating arrangement. That's all a crystal is just a repeating basic structure again and again. The more perfect the repeating structure, the more perfect the crystal is. So all of these ionic compounds are some sort of crystal structure. The ions are strongly bonded through electrostatic attraction. I mentioned that before. I keep mentioning it, so it's obviously a very important point. The structure is rigid and it has high melting points. Okay, so that means the structure is rigid. It's not soft, it's not bendable or anything like that. And then it has a high melting point. We're talking like really high temperatures, okay? Things you are not going to achieve on the kitchen stove. In terms of whether or not they conduct electricity, if you're conducting electricity, that means you have to have moving charges. Okay, moving pluses, moving minuses along those lines. In a solid, those ions are locked into place and they can't move. So since the ions are locked into place and they can't move, they cannot conduct electricity. So if I try to, conduct electricity using just salt, nothing's going to happen. Okay? But that's in its solid form. When it's melted, the ions can move around. Okay? So melted is also called molten, or sometimes you might see it referred to as the molten state. And then your ions are moving around because you have it as a liquid. And so if you try to melt table salt, salt melts at about 800 degrees Celsius. And once it's been melted, it will conduct the electricity. There's another way that ionic compounds can conduct electricity, and that's when they're dissolved in water. Okay, when they're dissolved in water, the cations and anions split, and they are free to move in water, and then since they're free to move, it's easier for them to conduct electricity. You will see this referred to as aqueous solutions. All aqueous means is dissolved in water. That's AQUEOUS. Okay, so that means that the compound has been dissolved in water, and in that case, it will conduct electricity. Okay, ionic compounds are brittle. So as I said before, they're rigid, they don't move very well. So you've got the pluses and the minuses there together, the positively charged ions and the negatively charged ions. And notice how they alternate. Okay, I've got a minus and then a plus, a minus and then a plus. And then the next row is layered the same way, but opposite. So that way the plus is next to the minus and, plus is next to the minus. You don't have two pluses next to each other or two minuses next to each other. So watch what happens in the picture if I apply some force and I push that first row. If I push that first row, then I've got pluses next to pluses. Well, like charges repel. They're repulsive. And so if I try and push the ions, then you get a strong repulsion. And what happens is it breaks the crystal apart because you have similar ions next to each other. So this is how you break or grind salt and other ionic compounds. Okay, so if you apply that pressure there, it puts like charges next to each other, and they don't like that, so they repulse, and when they push away, that's when it breaks. Now, metallic bonds are kind of an odd form of bonding. It's a separate category, and it just describes how metals are held together within a solid. Metals don't hold on to their valence electrons very well. Okay, so they have a very weak hold on their valence electrons. So now I'm talking about like your transition metals, the ones in the middle that I crossed out on the periodic table and I said don't worry about them. You're still not going to have to count the valence electrons, but you're going to have to understand how the electrons are positioned. And so essentially what you have is you have those positive ions still, your cations that are floating in a sea of electrons. Okay, so those valence electrons are much more mobile. So you can see here, I've got the positive ions, again, kind of layered apart, so there's some distance in between them. But now I have those little yellow dots, which represent that sea of valence electrons. And so those electrons are free to move through the solid. And since the electrons are free to move, metals are able to conduct electricity. This also allows metals to be malleable. Okay, malleable means it can be hammered or bent into shapes. Okay, because you're stretching it at that point. Metals are also ductile, and what ductile means is it can be drawn into long, thin wires, like copper. Copper is what we use to make wires that carry our electricity. Okay, so if you open up like an extension cord, or if you've seen the wiring inside your house, it's all copper wiring. Now, what explains both the malleability and the ductility is that sea of mobile valence electrons. Since the electrons can move, it allows things to be kind of stretched and bent, whereas in an ionic compound, they were not mobile. They were in a very tight, organized pattern. And so if you tried to stretch it or bend it, it would break. But with metals, it's different. And they can stretch because of the electron's mobility. Okay, so in this case here, it's a similar picture. Now I have my cations, my pluses, and those valence electrons. And this time when I apply my force, something different's going to happen. It just kind of glides like ball bearings in oil. So it just kind of slides back and forth. So I'll show you again. It there, and now I push it, and the electrons just kind of help grease the wheels and move along the cations into a different alternating pattern. Notice I still, for the most part, don't have pluses on top of pluses. It just kind of helped roll them to the next position that was most favorable. So now in this vodcast here, we covered ionic and metallic bonds. We also answered question 3. We started to answer question 3. What are the differences between ionic and covalent bonds and compounds? So we learned about ionic compounds here. What is metallic bonding? We just covered that. Why do atoms exchange electrons, and then what holds ionic compounds together. So a lot of questions there. The next two vodcasts are going to cover covalent bonding and then how to draw those Lewis structures.